Okay, so I mentioned in chapter 15 that chapter 16 will still all be about integration, but instead of integrating scalar functions, we'll often be integrating vector functions, or which they'll call vector fields. We won't do any integration yet in 16.1. We'll start that in 16.2. But first, we're just gonna like learn about vector fields. And so it says in meteorology, weather maps sometimes show the wind speed and direction at different locations. Each location gets its own vector that indicates the direction and velocity. Such a map is called a velocity vector field. So like I used to live in Texas, and they actually used to show the wind vector fields in the newscast and the weather forecast all the time. And so it would be, like a short arrow would mean it's not very windy, and then like a longer arrow would mean it's really windy. Maple, so I use Maple to produce this vector field. Maple will usually use the same size arrow all the time. So you may not be able to tell magnitude. You can tell direction, but you often can't tell magnitude. There are some commands you can put in, and it will like do gradation. So like bolder means stronger. So like on the second page of this, you can see that some of them are almost look like dots. So that means very, very small magnitude. And then so the ones that are longer. And then some of the other ones, they look like they're all about the same length. So if you look at wind, like a map for the wind, that map is called the velocity vector field. They're also used to show the behavior of ocean currents, airflow past an airfoil, and force fields, whether gravitational, magnetic, or even electrical. That's like a big application in physics too, looking at electrical fields. So it says, we may want to calculate the amount of work done moving an object or a particle through a vector field. Like one example here is sending a spacecraft into orbit against the Earth's gravitational field. Okay, so first definition, let D be a set in two-dimensional space of real numbers. A vector field on R2 is a function, f, that assigns to each point x, y in that set D a two-dimensional vector f of x, y. So like here, like if we look at the point 2, I'll just say 2.4, then we get this vector. So it's saying if that was a velocity, it would be heading, what, southeast? We can't really tell the magnitude from the picture, but you could find it if you had the actual vector field given. Since f is a two-dimensional vector, we can write it in terms of its component functions, which they call p and q, which are both functions of x and y. So you can have y's in the first component and x's in the second component. So a lot of times we'll just suppress the function notation. We'll just write p, I, q, j, or we can also use bracket notation. Okay, so it says p and q are scalar functions of two variables. Scalar function means the output is a single number. Like if you had p of xy equals 2xy plus 3y squared, if you plug in a point xy, you get one number as your answer. Whereas f, you plug in one point and you get a vector out. And sometimes they're called scalar fields to distinguish them from vector fields. I don't ever call them scalar fields, I just call them the component functions. And then the definition of a vector field on R3 is just you extend it so that you have one more component. Okay. So 4 says sketch the vector field F where this is the definition of F. So when I'm asked to sketch a vector field, well, first of all, it's tedious and I usually get Maple to do it, but here we'll do one by hand. So we'll plug in some values for x and y, and then we'll say what p and q are equal to at those values of x and y. And then I'll just make a column for the vector. Okay, so I for sure want to pick at least 1 point from each quadrant, and probably also a point on the axes, both positive and negative x and y. So maybe I'll just start with 2, 0. So I'm right on the positive x-axis, and then I'll pick a point in quadrant 1. Let's do 2, 2. And then I'll pick a point on the positive y-axis. This time let's just do 0, 1. And then in quadrant 2, let's do negative 2, 2. And then on the negative x, let's do negative 1, 0. And these are just arbitrary. And then in quadrant 3, let's do negative 2, negative 2. And on the negative y, let's do 0, negative 2. And then in quadrant 4, let's do 2, negative 2. And I might have us do a couple other points at the end if I feel like we need some more to get a complete picture of what's going on. So what is P? Yeah, P is x minus y, and Q is just x, right? I'm going to go ahead and just fill in the Q right away. So it would be 2, 2, 0, negative 2, negative 1, negative 2, 0, 2. Okay, so now the P. So what would the top one be? And then the second one, 0, and then 0 minus 1. Negative 2 minus 2 would be negative 4. Negative 1 minus 0. Negative 2 minus negative 2. 0 minus negative 2. And 2 minus negative 2. Okay, so the vector, the first vector would be 2, 2. And the second would be 0, 2. The third would be negative 1, 0. Negative 4, negative 2. Negative 1, negative 1. 0, negative 2. 2, 0. 4, 2. Okay, so we go to the point 2, 0, and we draw in the vector 2, 2, which means we go right to and up to. So here's 2, 0, and we go right to up to. And then at the point 2, 2, we have the vector 0, 2, which doesn't go left or right, only goes straight up 2. And then at the point 0, 1, we go left 1, and there's no vertical component. And then negative 2, 2, we go left 4, down 2. And then negative 1, 0, we go left 1, down 1. And then at the point negative 2, negative 2, we don't go left or right, we just go straight down 2. And then 0, negative 2, we go right 2, but no vertical. And then at 2, negative 2, we go right 4, up 2. And so, like, what Maple does, though, when it produces a vector field is it, like, does tons of points, right? So I kind of want to get an idea of what's going on here. I sort of see, this will come back like in the second half of the chapter. There almost seems to be some sort of tendency toward counterclockwise rotation. Do you see that sort of? No? Like, okay, at this point you see you're going that way. But here's the thing. Whenever we're on the line y equals x, then at some point you're going to end up going vertically, right? It's just they get more and more vertical, right? When you're on the line y equals x. So like if you were at the point 1, 1, you would go over 0, up 1. Okay. If you were at -1, -1, that would be 0 and the x would be -1. So all along the line y equals x, those points have no horizontal component. Then when we're on the y-axis, the x is 0, which means the second component will always be 0, which means there's no vertical part to it. So they're all horizontal, right? And if the x is 0 and the y is positive, then it's going to the left, right? And they just keep getting longer and longer. And in the bottom half, they go to the right. And if you're right on the x-axis, right, where the y is 0, then you just get the same vector. I mean, you get the same component both times, x, right? So you either get 1, 1, 2, 2, 3, 3, 4, 4, right? Or if you're on the negative side, -1, -1, -2, -2, right? So as you fill it in a little bit more, you can sort of see that there's this counterclockwise notation. I'm not ever going to have you, like on a test, do a vector field by hand because it's just tedious. But that's how you produce it. I'm more likely to have you do stuff like this, or what I have on the next page, where I give you the vector field and you have to match it to its graph. And these are 3-dimensional. I would never even try to produce one by hand. So usually what I do when I'm trying to match something is I look and I see if any of the components are constant. So like if I just put this in bracket notation, what would it be? Y -2x. So I'm focusing on this one, is the one in the middle is constant, which is, okay, it's like affects the y direction, right? So if y is -2, the y component is -2. That means every single one of my vectors should be pointing to the left, right? So all point left. Now's where it gets kind of tricky because the x is in the z, right? And so you think of, okay, so x, if I'm in the front half of the graph, which is where x is positive, that means the last component is positive, so it should be pointing up. So the vectors should point up in the front half. And then down in the back half, right? Because if we go back, the x is negative, so we'll have a negative number in the last component, which is like the z. Sometimes, like for me to just put one view on the paper, it's a little bit tricky. So Maple, this is where Maple is really nice because you can rotate these and see what they're doing. But just based on, well, I guess I should look at the y as well. So if y is positive, that means we're in the right half of the graph. So in the right half, the first component will be positive, which means it's pointing forward. Does that make sense? Okay. So forward in the right half. And then when y is negative, that means we've gone to the left. And then if the first component of my vector is negative, that means the x is negative, so it's pointing towards the back. So backward in the left half. So putting those things together, do you think it's graph A, B, or C? Actually, it has to be B. Before I even looked at any of the other two components, I see every single one of those vectors is pointing to the left. Okay, so this goes with B. Okay, so F, if I put that in bracket notation, it would be Y, Z, X. So the Y is in the first and the X is in the last. And I've already talked about what that means in terms of the vector field. And now Z is in the middle. Okay, so if Z is positive, that means we're in the top half of the graph. In the top half, that means the middle component of our vector will be positive. Let me see if I can. The focus is not as nice as I would like it to be. Then that's the Y part of the vector, which is left and right, so they'll point to the right. So in the top half, the vectors point to the right. But in the bottom half, right, which is when Z is negative, then they would point to the left. So out of A and C, which one seems to fit that? So here I think here's what's tricky about C, is I only give positive values of Z. I don't give any negative values of Z. So there's not really like I'm not showing you the bottom half of the plane. Oh, and here those Z's don't show on there, but they are actually negative 1 to 1, zeros in the middle. Is that right? Okay. Yeah. So I'm going to look at because a lot of times the easiest thing to see from the picture is whether they're pointing up or down. I'll show you an example where sometimes you think front and back should be easy, but I'll bring up Maple and show you one that's actually on the group work. So look at this graph right here. Does it look like those vectors are pointing forward or backward? Does it look like they're pointing towards the front of the room or the back of the room? That's what it looks like to me. Let me see if I have one. It's going to make me sign in. Okay, so I have this one saved actually. Come on. Okay, so there it is up here, right? So here it is on Maple, and it looks pretty much the same. I think I might have it like that. But now see when I rotate it, So here's the x-axis. You can see they're all pointing towards the front. So the key there is you don't really need to know so much whether they're pointing front or back. What can you tell me about every single vector in that graph? They're all pointing the same way. They're all parallel to one another, right? Nothing ever changes. So that should make it easy to figure out which one it is. Okay. So, okay, let's look at the last one, and then we'll compare these two here. So if I put this in bracket notation, I have y over z, negative x over z, and z over 4. So when I look at the first two components, and I have z in the denominator, so that's why one of the graphs doesn't have z equals 0 because it's undefined at 0. But as z gets big, those components, like if the y and x are staying constant, those two components get less and less. But the third one gets bigger and bigger. When z gets big, the third one gets big. But the first two will get smaller and smaller, which means there's almost no forward or backward motion or side to side motion, but there will be a lot of vertical to it. So using that idea, when I look at A, the higher up I get, it looks like the flatter my vectors get, right? So this one wouldn't go with A, but this one, the higher up I get, the more vertical the arrows get. It seems to have very little side to side or back and forth. It seems mostly vertical. You could do some other stuff too, but so this last one, the last function goes with C, the first one goes with A. And so I'm going to go back and look at A for a minute. So the y in the first component says forward in the right half, backward in the left half. And that part is really hard to see because it almost looks like these are right half, forward in the right half. Well, you can sort of see they're pointing maybe a little bit forward, although this one starts to look backward. The x in the last component says up in the front half. Okay, that part is easy to see. And then down in the back half. Yep, that makes sense. And then in the top half, vectors point right. Yep, that seems reasonable. And in the bottom half, vectors point left. That seems reasonable. Okay. All right. Okay, and then the other topic here is gradient fields. So if f is a scalar function of two variables, which means we have like f of x, y, then how do we find the gradient vector? What's the first component? F sub x. Yep, f sub y. And if we went into 3 dimensions, whoops, we just add that third component. Then it is a vector field on R2 because you'd plug in a point, x, y, and you'd get out a vector. And it's called a gradient vector field, okay? And then we could extend to 3 dimensions. So here we're asked to find the gradient vector field for each of the following functions and then match it to its graph. Okay, and one thing I want to warn you about that's what I have you do on the second page of the group work. So I give you 4 functions and 4 graphs, and I'm going to explain how to help narrow it down. But 2 of these, so what I'm going to, actually I'll come back to this, but keep this handy. Okay, so first I want to find the gradient. Okay, for the first one, what would the first component be? 1 over x plus 2y. And what would the second component be? 2 over x plus 2y. Okay. Oops. for the second one. What do we do to find the first component? Product rule. And I know I'm going to have an e to the negative x both times, so I'm just going to factor that out. Okay, so it'd be first times derivative of the second would be negative e to the negative x plus the second times the derivative of the first, so that'd just be plus 2x. And then what's the second component? 0. Okay, and then the last two are functions of 3 variables. Okay, so here, obviously the top two are only in 2-dimensional space, so they go with the top 2 graphs. And then the bottom 2 are 3-dimensional, so they go with the bottom 2. Your 4 are all in 2-dimensional space, and this one typo, that r of x should be r of xy, of course. Okay, so actually let's look at the 2-dimensional ones first. The thing I notice right away is for the second one, the second component is 0, which means there's no vertical component to any of the vectors. So would that go with the first graph or the second graph? The first graph, right? They're all horizontal. So I'm just going to call this 1, 2, 3, 4. Okay, so this goes with 1. Now, which means this one goes with 2, obviously. I want to talk about, though, why we have these big vectors right kind of through the middle and all the other ones are really small. Well, think of, okay, so this fraction, they just have constants in the numerator. So as the denominator gets big, the fraction gets small. So as you go away from the origin, your vectors get smaller and smaller. That's why they look like dots. Okay, we run into trouble when what happens? When the denominator is 0. So this x plus 2y equals 0 would mean x equals negative 2y or 2y equals negative x, which means y equals negative 1/2 x. That's where we get 0 in the denominator. And as the denominator gets smaller or closer to 0, the fractions get bigger, right? And here's the origin right in the middle. And see, if I go down 1/2 over 1, I end up here. So all of these big arrows are where the denominator is equal to 0. Okay, now for the 3-dimensional thing. So I would think of this as x squared plus y squared plus z squared to the 1/2 power, and then we'd use the chain rule. And so I know every single component, I'm going to get 1 over 2 times the square root of x squared plus y squared plus z squared. So I'm just going to factor that out in front. There's my 1/2 x squared plus y squared plus z squared to the negative 1/2. I'm going to get that every time. Then what would be left for the x component of the gradient? 2x. And then for the y, it'd be 2y. And for the z, it'd be 2z. So if you want, you can use this 2 to cancel out all the 2's there. Okay, let's look at the second one. What's the first component of the gradient? Cosine y over z. And then the second component, so x is a constant that stays out in front. The derivative of cosine is negative sine. What else would I need? 1 over z, so I'm just going to call it negative x over z. And then the third, so x is still the constant that stays out in front. The derivative of, I'm going to leave a little bit of extra space. The derivative of cosine, just like before, is negative sine. But now what would I have to multiply by? This is, right, so we're taking the derivative with respect to z. Derivative. Negative y z to the negative 2, right? So negative y over z squared. Okay, so this one I can do pretty easily. Like here again, I know when z gets big, well, sine is always between plus and minus 1. So I either have x or xy in the numerator, but when z gets big, those fractions get small. So when we get really high, then the vectors should get almost flat, right? There will be almost no vertical component to it, right? Or in the middle, if z is really big, so that means almost no left and right, everything will be forward or back, right? And so when I look at graph 4, I see that they're all at the top, they're pretty much almost all going forward. So this one would go with 4 and this one would go with 3. I want to talk about a way that you're going to need to use on the group work though. So what you're going to want to do is you want to look at a corner. Because none of these have like a part where it's always flat. They're not always going the same way. Some are going to the right and some are going to the left. Some are going up and some are going down in every single one of the graphs. So nothing stays the same all the time. So what you want to do is pick a corner. And here, like if I were in 3 dimensions, which you will have to do, like this one is easy, and then this one actually, you shouldn't ever have to worry about picking a corner because one of the components is always constant. But if they weren't, maybe I'll bring up some WebAssign problems. What you want to do is pick a corner where you can tell they're doing something different. So like on this first page, if I wasn't able to rule some of these out at the beginning, and I was just trying to base everything on the formula, I have kind of, well, technically we have 8 corners, but the like back corner and the front corner are often really hard to see because there are vectors either right in front of them or right behind them. So you kind of have 6 corners to pick from. You want to pick one where they're doing different things. So I wouldn't necessarily want to pick this back corner because it looks like they're all doing about the same thing based on the picture. It looks like they're all kind of going up and to the right, up and to the right, up and to the right. So it wouldn't help me to pick a back corner, that back corner. But what if I pick this corner? If I'm at this corner, what's the x coordinate of that corner? Yep. And here we see the x-axis, so it would be positive 1, right? And all of them have the same scale, so the x is 1. What's the y? Negative 1. And that's true for all of them. And what's the z? Negative 1. That's true for all of them. So what you would do is you would plug this point into each of these 4. And then this one, so what would you want the first component to be? Positive or negative, does it look like? positive because this one's coming forward. Would you want the middle component to be positive or negative? So yeah, because it's pointing to the left, right? And what about the third component? Negative, because it's pointing down. Right? Oops. Let's look at the one above it. Okay, this is the one that's deceiving, right? It looks like it's pointing backward. So from this picture, it sort of looks like negative, but remember I showed you the picture where it's really not negative. What about the middle? Do you think the middle should be positive or negative? Positive. It looks like it's pointing to the right. The third component for sure you want to be what? Positive. It's definitely going uphill. That part is not up for question. So we can see that the last components are different and we think the middle components are different, okay? What about this one? Do you think the first component should be, well, in here I'm gonna say or zero, positive, negative, or zero? There's a reason I added zero. Because it doesn't look like from the picture that it's going either forward or backward, right? It's really hard to tell. Okay, what about the middle? Positive, because it's pointing to the right. And what about the third? Negative, because it's pointing downhill. So this one, the last components are the same, but the middle are different. So I should be able to distinguish between those two. And from these two, the last components are different. So that should help me narrow it down. And then the last one, what do you think about the first component? I have an idea, but it might not look the same to you. Do you think the first component looks like it should be positive or negative? I think positive. It looks like it's pointing forward to me. What about the middle component? Negative. And the third component? Positive. So see, they're all different. So if you plug that point in, you should be able to, as long as you're, you choose a good corner. Like I said, that wouldn't have happened if you chose this corner right here because so many of them look to be doing the same thing. You want to pick a corner where they're all doing something different. So when you look at the group work, would it be smart to pick this corner? 3 of the 4 are doing the exact same thing, so don't pick that corner. Or, I mean, you could, and then you know for sure which one this is, right? But it'd be nice if we could find one where we could get more than one answer to start out with. What if we look at the top left? Yeah, that wouldn't be bad, right? Because this one down and to the right, so positive, negative, I should say to the right and down because that's the order we do them in. This is to the left and up, so it'd be negative, positive. So these two are the same. And then this one is left and down, right? So this one would be a good corner to check. We'd still have to focus on these two, but if you look at these two, every single corner is the same. So you can't use corners for this one. So what is then the main difference between this graph and this graph? What's happening where? At the origin, right? Because one of them is almost 0 and the other one is big, right? So you should be able to get these two from this corner. And then for the 2 that are left, you'll have to look at what's happening at the origin. Okay. So this will come into play later. Have either of you taken Physics 2 yet? Yeah. So this is like a electrical fields and equipotential surfaces, where like the lines are like, those are like the equipotential surfaces, like the voltage. Does that sound familiar at all? Okay. And then these are the electrical field lines. And the same here. Like if you had a charged particle or whatever, then the farther away you go, the weaker, like, or the less voltage is, right? So these are almost like level curves, right? Like for, here's where the voltage is constant, and then you have a voltage drop, and here's another line where the voltage is constant, and so on. And these are the electrical field lines coming out from the sources or whatever. Okay, so here's one function, f of x squared plus 2y squared equals 1. And then here's another function that's like this really complicated function. Okay, so it says their gradient vector fields along with several level curves are shown below. So this one, it would be really hard to, I mean, not hard, but it would just be really tedious to find its gradient. But we can do f pretty easily. What's the gradient for f? What would the first component be? 2x, and the second 4y. So that means in the first quadrant, x and y are both positive, and so both of these would be positive. So in the first quadrant, the vectors should be pointing to the right and up, which it looks to be true for both of these. In the second quadrant, x is negative, y is positive, so they should still all be pointing up, but to the left. And so you see that's happening here, which is not happening here, right? So the first one goes with f, and the second one goes with g. The level curves, well, think about what is the graph of f of xy equals x squared plus 2y squared plus 1. If I were to graph that, I'd get a what? So think of if it was just z equals, what if it was just z equals x squared plus 1? What would that graph be? Well, I'm just talking 2 dimensions. If we were just graphing in 2 dimensions, a parabola, and if I graph z equals 2y squared plus 1, I'd get. If I just did z equals 2y squared plus 1, it would be parabola. So parabola, so it's a paraboloid, right? And so these are, like, I'm doing slices parallel to the floor, right? So I have my paraboloid, and here are my level curves, okay? The most important thing about the relationship between the vector fields and the level curves you should see in the picture. What do you notice about the level curves and the arrows? What's the relationship? No matter where you look. So look at any point where an arrow touches a level curve. What's true? They're perpendicular, right? So the gradient field is always perpendicular, or the gradient field vectors are always perpendicular to the level curve. All right, and I was just going to see if there's anything. I think the WebAssign, I think a lot of the 16.1 is matching. Okay, so there are 9 questions. Yeah, so like here, again, you could just kind of use, well, if y is positive, we're in the top half, then the first component would be positive, which means pointing to the right. So in the top half, all the vectors should point to the right. So it can't be the first graph. It could be the second graph. It could be the third graph. It could be the fourth graph, right? So now I look at the second component. So if x is positive, which means we're in the right half, the vectors should be pointing up. So in the right half, all the vectors point up. So 2 works. Actually, it looks like 3 works, but not 4. So it's between 2 and 4. And then notice that in 3, the vectors close to the y-axis seem to have pretty big magnitude. So close to the origin, they have big magnitude. But in graph 2, close to the origin, they have small magnitude. What do you think it should be based on this? Big magnitude or small magnitude close to the origin? Small. So it's got to be this one. But again, you could just plug in points too, but. Okay, then 1 comma sine y, all of the vectors have to be pointing to the right, right? If the first component is 1, so you can automatically rule out some of those. This one, there's no y in either component. So that means it doesn't matter how high or how low you go. Like if you pick an x value, you'll get a vector, and then all of the vectors above and below that should look the same. Does that make sense? So like if I look at this one, everything below it looks just like it. If I pick this one, everything below it looks just like it. Same thing here. But this one, if I go below it, nope, they get smaller and smaller and they change. So it can't be the second. This one they change. I mean, they get smaller. And this one they change. So the only one it could be is the first one. And again, if that doesn't make sense, you can always pick points. Let's see, I'm just gonna hit submit. Make sure everything I guessed was right. So far, did I only guess for 2 of them? Yeah, okay. And then I see that 3 over x in there, which means as x gets big, that second component will get small. So farther to the right, farther to the left, not so much of vertical motion to the arrows, which means it should be the third graph. Okay. This one walks you through, this one walks you through. Okay. This one, it only has a k component. So the x and y are both, there's no I or j, so those are 0. So there should be no front and back, no left and right. And the third component, the vertical part, depends on the y coordinate. So if y is positive, we're in the right half of the graph. So it should point up on the right and down on the left, right? Which means it looks like it's got to be the first graph then. Yeah. Yeah. Okay, and then the second one is similar, it's just they put a negative x in that third component. J minus I, so that means they just switch the order. There's no vertical, so they should be all horizontal. And then the I has a -1, so they should be pointing backwards, and the J is +1 and to the right. So it looks like it should be the first graph. Oh no, not the first graph. Those have a vertical component. It should be the third graph, sorry. 2, 3, 4, everything is constant. So which graph should it be? First, second, third, or fourth? It has to be the second one. And then for 8, I think that's one kind of like on the group work. I don't really care so much about the x and y first. I noticed that the last component is 3, which means every vector has to be pointing up. So right away, I know it's one of the top 2, right? But this one, they're always pointing to the right. And This one, it should not be pointing to the right. It should be pointing to the right in the right half and pointing to the left in the left half. So it's the first graph. Okay, and that's just find the gradient, which we've done before. All right, that's it.